Okay, hopefully this is the last segment for this unit. You see that the sharing of electrons is much more problematic than just simply making ions. So the lion's share of this unit has really been about talking about what happens when we share. And so ultimately what we're looking for is a net dipole that occurs in the entirety of the molecule, not just a bond itself. So again, we need to take the instances in which we get shared electrons, come up with a Lewis structure, come up with polar bonds, come up with the shape, and then look for the net dipole. Our last thing to talk about, we talked about resonance, which is the movement of electrons. So you should be looking on your lab sheet which of the structures will show resonance. Isomers come from a different arrangement of atoms. Okay? Now our three resonance structures of carbonate, for the simplicity of this, I'm just going to use nitrate and move on to isomers. Okay, so I should have enough atoms here with the models that I have at my house to make my point on this one. So C2H4Br2, we get something like that when we draw our Lewis structures, and we need to make sure that our carbons are linked together. That's our rule. And then we fill in to make carbon happy. Okay, so for example, what students would usually do is they would come up with a structure like this for C2H4Br2, making it symmetrical. Okay. Here, I'll draw it this way. 2 carbons, 4 hydrogens, 2 bromines. Okay, now notice on this that I can point these bromines any way I want because the bonds are free to rotate. So I'm not creating anything new here because I'm not breaking any bonds. However, what I can do is I can take the bromines, and instead of them being on an individual carbon, I can break a bond. Okay, so I'm breaking the bond, break the bond, and I'm going to move the bromines onto the same atom. Okay, now notice that I can put them on this carbon or I can put them on this carbon. I'm not breaking any bonds, so it doesn't make any difference if I write my bromines this way or whether I write my bromines this way. These two are the same, so I'm going to cross that one out. I'll put the hydrogens in. And the relationship between these is that these are isomers, and they're specifically called constitutional isomers. Okay, when you get to biochemistry, you will learn that there are multiple kinds of isomers. Constitutional is the easiest one to perceive by the movement of atoms. So we're going to start there. Okay, so I could start with C5H12. Okay, first thing I would do is link those 5 carbons together. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I'm just going to leave the H's out for clarity. This would be the simplest rendition of this. Okay, so now what we're going to do is we're going to move carbons around. Okay, and I don't have 5 carbons with me, so I'm just going to draw. And I'm going to make some different renditions that students will do to make my point. So if I take 4 and I pull one of these carbons off, I can put that 5th carbon anywhere on my structure. And oftentimes, students will say, put the carbon on the end. So I'm going to put the carbon on the end. And what we see is 1, 2, 3, 4, 5 carbons linked together. 1, 2, 3, 4, 5 carbons linked together. This is the same as this. So this is not an isomer. That's the same thing. I can try again and put my 5th carbon second from the end or second from the end. Okay, it doesn't make any difference. And now I have 4 carbons in the longest continuous carbon chain instead of 5, and I have 1 that is a branch. So this is an example of a constitutional isomer of this, or I could say these 2 are constitutional isomers. Okay, I could draw 1, 2, 3, 4, 5. I could arrange them this way. My longest continuous carbon chain, okay, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Regardless of which ones I circle, I have 3. So I'm going to be a rebel, and I'm going to circle those 3 and say I have 3 in the longest continuous carbon chain and 2 that are branches. So this is also an isomer. Or stated differently, I would say all 3 of these are isomers. Okay? Now the last thing I'm going to talk about is this net dipole. And I'm going to see if I can do this in the remainder of this video. Okay, so the net dipole means, do we have a net separation of charge? Okay, so what this means then is you need to go and look at your Lewis structure. So for example, I'm going to take water. So water, the Lewis structure of water looks like this. 4 areas of electron density, 2 lone pairs. We would determine that water is bent. So I'm going to draw water as bent because that's what the structure says. Then what I would do is I would have my polar bonds, yes or no. I would see that oxygen is partially negative, hydrogen is partially positive, and you should have done this on your lab sheet already for all the structures that you have. So now I'm going to put this polarity into my molecule. Partial negative, partial positive, partial positive. Okay, so net separation of charge means, do I have a net separation of charge? And I'm going to determine that by drawing what we call vectors. So vector, okay, these are vectors. We draw the positive with the positive.